Hey, Tori. Hey, Haley. Did y'all get a chance to look at your test yet?
Yeah, I did.
Okay. I'm going to put a key online soon, everybody. So you'll be able to see what the exact answers were. Tori, did you get a chance to look at yours?
I haven't yet, but I got your email.
Okay. All right. As usual, I think you did better than you thought you were going to do. I don't know.
Okay, good.
Well, if that makes you more liable to look at it.
I will definitely go look at it.
Okay. All right. Okay, who else is trying to come in? Stephanie's trying to come in. All right, there's Stephanie. Hi, Stephanie. I don't know if she can hear me yet.
Hi,
Yeah. Doing okay?
I am. Thank you. How about you?
Okay, one day at a time. Yep.
We're making it. Not much more to go.
What's that? Not much more, I know.
Yeah.
Counting down the days here. We got less than 2 weeks, and really that's less than a week in a way. We're just going to do new material through next week. We're not going to do anything that partial week. So we're not going to. We'll do a review or do what we have to do that week. So. All right, let's see here. Let me go ahead and share the screen. Maybe we'll get a few more people in a minute. And sort of look at what we were doing yesterday. And then we're going to do something entirely different today. Okay. There we go. Okay. So let's just get back to where we were yesterday for a minute. What we did yesterday was look at a couple of things. We looked at this e to the x, which we said was its own derivative. And then we looked at a sort of a more general rule where we said if we had e to a function of x, it repeated itself like it was its own derivative, but then it had to multiply by the derivative of whatever that power was. So guys, the homework last night predominantly, and I still didn't quite finish this lecture, but the homework last night was finding some derivatives of these things. So for those of you that are here, did anybody have any trouble finding derivatives for that? And that's really all we did. And I'm gonna give you a quiz over the weekend so that you get some practice with this. But it's really just basically those two rules mixed up with all the other rules, quotient rule, product rule, and so forth and so on. So let me get back to where the homework was. The homework was in 4.3, I think. Did anybody?
Can we do problem 13?
13, okay, let's do that. 13, and it was, well, I'm about to find the page. It was on page 273, okay? Okay, that's a good one. Let's do 13. Okay, so the function, get everything organized here. The function in 13, so we've got this, f of x is equal to e to the 3x plus 1. No, not just e to the 3x. E to the x plus 1 over e to the x minus 1. Is that the one you're asking about, Haley?
Yeah.
Okay. All right. So guys, I don't think anybody else is trying to get in. What you want to look at on this problem, e to the x is just a new function. All our old rules are still in place. So when you look at a problem like this to begin with, you say, well, I need to think about what the structure of the problem is. Well, the structure of the problem is a quotient. So what we're going to have to do is use the quotient rule. Okay, so let's play the quotient rule out, and then we'll see. The problem might be in simplifying it, but we'll check it out. So the quotient rule says the bottom times the derivative of the top. Well, guys, if you look at this thing, we said that e to the x was its own derivative, so that's going to be e to the x. And of course, the derivative of 1 is 0, minus the top, e to the x plus 1, times the derivative of the bottom. Well, the derivative of the bottom, again, there's an e to the x, so it's its own derivative, and the derivative of minus 1 is 0. So there's an e to the x right there. And it's going to be all over e to the x minus 1 squared. Okay? So that's the basic way that it plays out. I do want to simplify this, but Haley, your question, do you see what I did here?
Yeah.
Okay. Did you get this far, or was it a?
I guess it's just hard since these problems, like, I've forgotten about the question and the
Okay,
other
all right.
rule. Like, when I look at one, I don't really know where to start.
Okay, so really we've really only got several rules. We've got power rule, which applies to old functions. We got this new function, e to the x, it's got its own rules. And then you've got to see if it's a, you know, if it's a bunch of things added or subtracted, you can just go down the line taking the derivative. But if it's a product or a quotient, we got to use the product rule or the quotient rule. This is good. This is one reason I picked up this section right here, because I need for you to be reminded of the stuff that was way earlier in the course, way back when we were sitting in a classroom. Okay, so you see that's a quotient. That's why you got to use the quotient rule on it. There's nothing else you can do to it. If I were to simplify this, guys, it's not that hard. E to the x times e to the x. The rules for exponents work exactly the same as they do normally. If you've got a like base, you add powers. So that's e to the 2x. You just add x to x. And then minus e to the x. This next one's going to be minus e to the 2x, because of that minus there, and minus e to the x. And it will all be over e to the x minus 1 squared. Couple things drop out. Those two drop out. And then I've got 2 of those, or minus 2 of those. So minus 2 e to the x over e to the x minus 1 squared. Okay. Whoops, I'm getting dyslexic here. Hang on. That's minus 2 e to the x. E to the x. I put that together with that. Okay. Okay, let's pick another one that'll remind you of some more rules.
I also wanted to do the rate of change number 47 one.
Okay, all right, we'll do that. But I tell you what, let me do 15, because it's kind of a mixed up thing, and it uses a couple of rules. So let's try 15 as an example. Then I'll do the rate of change problem. Okay. On 15, this was on the same page, 273. The function was x e to the x. X e to the x minus 4 e to the minus x. Now, guys, when we have subtractions and additions, we're just going to do each one of these things separately. But what you need to notice in this one right here is that, and it's easy to miss because there's not much there. This is x times e to the x. That's two very simple functions, but they are multiplied by each other. I've got to use the product rule on that, all right? So y prime on this one is going to be first. The derivative of e to the x we know is just e to the x times the derivative, so it's first times the derivative of the second, plus the second, which we're letting be e to the x, times the derivative of x. And the derivative of x is just 1. Now I'm going to go ahead and do this one. So that'll be minus 4. Now, this is an example of our other rule. That's not an e to the x. Actually, it's an e to the minus x. You got to be careful. It does repeat itself, but it's got to multiply by the derivative of this power here. What's the derivative of minus 1 times x? Anybody? What's the derivative of that thing right there? What's the derivative of minus 1 times x?
Minus 2, no, minus 1x.
Minus 1. Minus 1. It's the coefficient on that, okay? So minus 1. So I don't know, if you were to simplify that, there's not much to do. Minus a minus would be plus here.
Now, how did you get the minus 1 again?
Okay, look. If I said to you, what's the derivative of 2x, what would you tell me?
2,
2. What's the derivative of 5x, what would you tell me?
5,
5. What's the derivative of minus x? Well, minus x is minus 1x. What are you going to tell me the derivative of that one is?
-1.
Right. That's exactly right.
So
Okay.
do we use a rule here?
Yeah, the rule we used in this one right here was that the derivative of e to the g of x is it repeats itself, and then it multiplies by the derivative of that power. So what your g of x was in this case, guys, was this minus x. So you see it repeating itself, and then the derivative of minus x was minus 1. That was this piece.
Okay.
Okay? That's the rule I'm using. If it's anything other than e to the x, just a plain old x, you got to multiply by its derivative. I'm gonna try one more because of that question here, guys. Is everybody okay on that one? It's a product rule is what I was trying to point out there. Another one, suppose I had e, and I'm making, this was actually number 8 on the same page. You had a function, y is e to the square root of x. Okay, that rule that I had right there says that the derivative on this thing repeats itself, but then you got to multiply by the derivative of the square root of x. Now I'm going to go over here and remind myself that the square root of x is x to the 1/2. Okay, its derivative is just going to be 1/2 x to the minus 1/2. Okay, 1/2 x to the minus 1/2. So I repeated it and then multiplied it by what was right here. Okay, the quiz, guys, some of the things that are going to be on the quiz are just, actually, it's just some of these things right here and a graph, which we've already done. I'm going to talk more about the graphs later. But it's just these derivatives. Haley, Stephanie, you okay? Haley and Tori and everybody okay?
Yeah.
It's the rule, and you got to remember you got the product rule and quotient rule there. All right, Haley, what's the one you wanted on the other page? It was 40 something.
It was the rate of change problem, which was 47.
Okay, good. Let's look at 47. That's a good problem. You'll see another one like that again. Let's see. So here's 47. On 47, it says the balance A in a savings account is 5,000 e to the 0.08 t. A is 5,000 e to the 0.08 t. Okay, which is measured, t is measured in years. Find the rate at which the balance is changing when t is 1. Now, guys, this is the formula. A equal P e to the RT. If I were just to plug a T into that, it would tell me what my money was at time T. So for example, if I said, let's let T be 5 in this thing, I'd have, after 5 years, and I'm continuously compounding, it'd be 5,000 e to the 0.08 times 5. And I just made that one up, so I'm gonna get my calculator and see. While I'm doing it, guys, y'all compute that and let me know what you get, and I'll compute it and we'll see how it compares. So 5,000 times, pick up your E with your second LN, put your power in, it's gonna be 0.08 times 5. And when I enter that, I'm gonna get 7459.12, I think. So the amount there, after 5 years, will be 7459.12. So it will have accumulated that much. Basically, that says when you have a 0.08, it says you're getting an 8% interest rate there. Okay, so that's not what the question asked, though. Here's what the question asked. Is everybody okay with what that formula means? That's that continuous compounding formula, where T is time in years, R is the rate. All right. If you look at what the question says, it says find the rate at which this is changing when time is 1. Now, anytime you see the words rate of change, what you know you're doing is looking at a derivative. We talked constantly about this from the beginning of the course. The derivative is a rate of change. So they're asking you to find the derivative of that thing. Okay, so the derivative of this thing, notice that's just a constant, it's 5,000. I really don't need to use the product rule on this because the derivative of a constant times a function is just that constant times the derivative of the function. Now, here's what I want you to do. I want you to take the derivative of this. And based on the examples we just did, it shouldn't be too hard. It repeats itself. So e to the 0.08t. And then it's got to multiply by the derivative of 0.08. This thing right here. What's the derivative of 0.08t, guys? We looked at this a minute ago.
0.08.
0.08. Remember, the derivative of 5t would be 5. Derivative of 10t would be 10. The derivative of 0.08t is 0.08. So what I'm doing is taking the derivative of that power right there. That's my g of x. That's my g prime of x. Now it's just a matter of multiplying this out. Let's see what it is. I'm going to multiply. Let me multiply the 5,000 times the 0.08 first, because those are just two numbers there. So 0.08. I'll just enter that. And then when do I get 400? So that's going to be 400 times e to the 0.08. And it asked me to do this to find this rate of change, first of all, when this was 1. All right, so it's going to be e, pick up that e, and raise it to the 0.08 times 1, which is just 0.08. All right, enter that, and what I get is 433.31. 433.31. I'd like verification on that, guys. I picked up a calculator that's got a bunch of lines through the screen. It's about to die. So 433.31. And I was just putting time 1 in for that right there. Is everybody getting that? Percent 400.
Yes.
Anybody getting it? Everybody? Okay.
Yeah.
Okay.
Mhm.
So guys, let me tell you what units it's in. It's in rates of change. Well, amount is measured in dollars. T is measured in time, in years. So this is dollars per year. So in other words, at the end of 1 year, my balance is increasing at $433.31 per year. Okay, per year. It asks a few more things. Let's just do one. Wow, after 50 years, that's a long time. I wouldn't leave money in the bank because I'd be afraid I'd be dead in 50 years. But anyway, there we go. Let's do it with 50 years and see. Because that means you have left that money in there a long time and it should have accumulated to a lot. So let's look at the derivative again is the same. It's a prime is that 5,000 that you put in initially. It's going to be e to the 0.08, and the time in years now is 50. And then remember, it was times this 0.08 down here. And we already did a little of the work here. 0.08 times 5,000 is still going to be 400. So e to the 0.08 times 50. Okay, I'm going to compute that, guys. Let's do that. So I've got 400 times e, and I'm going to put in 0.08 times 50 here, and I get 21,839.26. Okay, now again, that's in dollars per year at that point. Now, why is it so much higher? And it may look so high to you that you don't believe it, but it's true. Is everybody getting this? Can I get some verification on that, guys? 21,000.
Yes, I got it.
Okay, good. So you've left that $5,000 in there a long time. There is a big balance in here. I mean, if we wanted to know what the balance was, we could take that 5,000 and see how much it accumulated to over 50 years. Let's do that and then we'll compare what we're getting per year. So that's times 50. So that's what I would have, not the derivative, but that's what I would have in the amount in the account after 50 years. So let's do that. So 5,000 times E, and this one will be 0.08 times 50.
What are you doing?
I'm just figuring out how much money there is in the account after 50 years. This was the rate of change. This meant that at 50 years, you were getting almost $22,000 a year per year at that point. What I'm doing right now is going back to the original function and finding out how much I've got in the account. So let me put the figure down. We'll talk about it. Figure I'm getting is 272,990. 272,990.75. So two questions here, guys. That's not a question that they asked, okay? I just did it. If I said to you, how much money is in the account after 50 years, you're going to plug into the original function, okay, not the derivative. If I ask you for the rate of change, you're going to plug into the derivative. So this says, if I plugged into the original, it says after 50 years, I'm going to have close to $300,000 in this account. So the rate at which it's changing, you're getting basically this much interest, $21,839.26 per year, or dollars per year. So that's a big chunk. I mean, 50 years is a long ways away, but if you got $5,000 laying around and you think you might have grandchildren, put it in and say, hey, maybe you'll have this is my fund for you, for your college fund or something, okay? So, but that's why they call this the compound interest is the eighth wonder of the world. Things can stack up pretty fast if you leave your money and you let it grow. Okay, and that's why the rich get richer and the poor get poorer. Okay, because those of us who are poorer don't have a lot of money to lay away like that. But anyway, that's that. That's my social lesson for the morning. Okay, so all right. So everybody okay with that?
Yes.
Okay. So what we're gonna have for homework is just some of these problems, guys. Actually, one exactly like Haley just asked me here. This one is 47 in the rate of change, and then just a few to find the derivative of. And I've put it on Moodle. Let's have it due on Monday, and I'll send out an email about that since you guys are the only 3 brave souls that showed up for class this morning. All right, so you get a plus here. Okay. So what I want to do next, I want to do something totally different. So I'm basically through with exponents. Everything you're going to know this semester about exponents is kind of done here. What are exponential functions? What do their graphs look like? And so on. I did ask you to do one other thing last night, though. I almost forgot about. I looked at this one right here. And I looked at a function that looked like that. And I asked you to analyze the graph. And what we do when we analyze the graph is take a derivative, okay? And then we find out where it's positive and negative in order to find increasing and decreasing. I had to use the product rule on this one. So it was x times the derivative of e to the x, so this times the derivative of this, plus e to the x times the derivative of x, which is 1. I then pulled out e to the x, and then made the observation that e to the x is never negative, and it's never 0. The only place this thing's going to be 0 is at -1. So I test on the left and the right. To the right, it was increasing. To the left, it was decreasing. That means there was a local min there. I plugged in -1 to the original function, right there. And I got that the point there was -1 minus 0.37. If I wanted to find out about concavity, I took the second derivative. Starting from the first derivative, I ended up with a second derivative of e to the x plus 2. The only place that's going to be 0 is at -2. To the right, it's positive, so concave up. To the left, it's negative. Again, e to the x, guys, is always positive, and it's never 0. Never 0. When I plug -2 into the original function, I got this. What I left you with yesterday was I left you with a request to graph this thing. And I told you that the window on it, you need to make the window pretty small because the values are pretty small. The window on it, we said, let's go from -4 to 4 and -1 to 1. And what happened is you should have gotten a curve that looked like this. We had an inflection point. We had something that changed from concave down to concave up. That was that point -2, -0.27. And then it was concave up with a local min right here at -0.37. My scale's a little off, but I kind of ran out of graph down here. And then it kept going on up. It was increasing. So it was decreasing before -1, increasing after, concave down here, concave up here. So the master line, guys, on this thing would have looked like this. We had a -2 and a -1. Everywhere to the left of -1, it was decreasing, which we discovered up top. To the right of -1, it was increasing. To the left of -2, it was concave down. Whoops. Concave down. And to the right, it's concave up. So that's what you're looking at. Here's this shape, and this shape. You guys were pretty good on the shapes on the test. I think it part of it got lost where you say if you have a positive first derivative, that's what you got, those positives on that line. That means increasing. A negative first derivative in words just means that you're going to have a decreasing thing there. So that's what that looked like. Okay, so let's go back here. Everybody okay with that one? All right. Okay, so today I'm going to go on to something totally different, but not hard. I'm going to ask a question that is the following. I'm going to say we're going into chapter 5, and chapter 5 and 5.1 are entitled antiderivatives. And another name for antiderivatives are indefinite integrals. But I'm going to refer to them as antiderivatives because I think it tells us a little bit better what we're trying to do, at least initially. What we're going to do here is everywhere in this course, up until now, we've been given a function and asked to find the derivative. Now we're going to be given the derivative and asked to find the function. In other words, we're going back. We're going to do an antiderivative. So we're going to be given the derivative and asked to find the function. Now I'm going to start out with some easy ones, guys, and see how good you are at going back. And then I need a rule because it gets a little harder than this afterwards. Suppose you took a function, and everybody mic off here. I want to hear answers. Suppose you took a derivative and you found 3x squared. Do you know where that one came from? What function would that have come from? Anybody? Whose derivative is this thing right here? Remember what happens in a derivative. You bring down the power and you lessen the power by 1. So what would have given you this?
X to the third?
Yeah, I think Haley's got it. So check her, guys. If you've got x to the third, if you differentiated it, you'd get 3x squared. So we say that's the antiderivative of that. We say it's the antiderivative of that. Now, there is a notation that sometimes we use. Your book's not going to use it very much, but you sort of put an inverse sign there. The antiderivative of 3x squared is x cubed. So you start with the derivative, you anti-differentiate it, you get the function back. Now, I want to ask you a question, though, first. Do you know any other functions that would have that same derivative? Right there? Is there anything you could put with x cubed that would still give you that same derivative right there? I'll ask you this question. Do you know anything that would be, whose derivative would be 0?
A constant?
A constant.
So you
Everybody
could put
agree with
1
that?
with it.
Well, you could put 1 with it. You know, okay, so Haley says I could put 1 with it and it would still have the same derivative, wouldn't it? Is there another number I could put with it?
I mean, you could put any number with it.
Yeah, you can put any number there, guys. I could put 158. It doesn't matter because the derivative of 158 is still 0. So here's what we do in that case. What we do is instead of just putting a specific constant, we're going to put what I call an arbitrary constant. I'm saying, okay, well, some constant, but I don't know what it is, but there it is. Okay?
Is that C?
That's a C. And we call that an arbitrary constant, guys. An arbitrary just means it can be anything. Now, there is a way to find what constant it is, but we don't have enough information for that right now. All right, let's try another one. Whose derivative is 2x?
X squared.
Okay. So I'm hearing Haley, but Stephanie and Tori, you see what she's sort of looking at is, well, I would have had to bring down the 2 and have a 1 left, right? When I took away.
Right.
Okay, Tori, you okay with that?
Yeah.
Okay, so I would have had an x squared, but I also could have had any old constant on it, and I would still get it. So the derivative, and you can always check, you've got the right answer when if you differentiate this, you get back to that. So you're starting with the derivative, you're finding the function. All right, tell me whose derivative is 5. We talked about this. 5x, good. We've already talked about that today. So it's 5x plus a constant. It's 5x plus a constant. Okay, let's keep looking here. We'll do one more. How about 5x to the 4th? Whoops, I didn't go far enough up. How about 5x to the 4th there, guys?
X to the 5th.
Yep, x to the 5th plus c. Now, guys, the plus c is really important because what that says is that it could be any one of a number of functions. I didn't really understand when I was taking calculus the first time how important that was, and I kept leaving it off. And my professor kept deducting points, and I'm like, okay, I get it. Okay, I'm going to put it there because why deduct points when, I mean, it's a pretty easy thing to do. It's a pretty easy thing to remember why you do it. So you always want to put a plus C on these things. I got a special name for it in just a second. So that's what we get. So here's the definition of what I've been doing. A function f is an antiderivative, a function capital F is an antiderivative of a function little f if for every x in the domain of f, it follows that f prime is equal to f. In other words, that's an antiderivative of that. I should probably call that capital F there. Doesn't matter, but should probably call it capital F. Because I can check it. In other words, it's an antiderivative because when I take its derivative, I get back to that. So that's my antiderivative. Now, I said a second ago that often we use this notation, this d sub x. That means you're taking an antiderivative and your variable's x. What we would have had here would have been, again, we already did this. This was x squared plus c. This one was x cubed plus c. Now, that is only a notation we kind of start out with, and I'm going to leave it behind very quickly. And the notation that all books use, all calculus books use, is this kind of lazy s right here. There's a reason for this. And then a dx always goes with it depending on what if you're looking at functions in terms of x. This is called an integral sign, right? An integral sign. And if you see something behind an integral sign, then what you know is that you're trying to take the antiderivative. So the integral sign is just the standard mathematical notation for the antiderivative. Now, let me tell you why this dx is important. These two they're just notationally, they're paired together. It's saying that your variable's x. Well, you say, well, I could have seen that here. Yeah, well, okay. It's going to be x squared plus c. This one will be x cubed plus c. I could have had a t here. So the antiderivative of 2t would have been t squared plus c. Even more important, you showed me one a minute ago. Look at that one. If I said, whose derivative is 5, you told me a minute ago it was 5x because we're so used to dealing with x's. But if I'm doing something that has to do with time, then I might want to integrate this with respect to c. In other words, it's, I'm sorry, not c, but t. So it's coming from a function with a t in it. So instead of being 5x, it's 5t. Okay, so that's what that tells you. It tells you what function, what variable you're working with here. So if I said, what's the integral of 5x to the, no. Let's do this. Let me start that again. If I said, what's the integral of minus 10 dp? That would mean I'm working with variables that are called p's. So what's the integral? Whose derivative is minus 10, guys? Whose derivative is minus 10?
Minus 10x.
It's usually minus 10x. That's right, because the derivative of minus 10x is minus 10. But this thing right here tells me that I'm not dealing with x's anymore. I'm dealing with p.
P, so it's minus 10p.
Yes, so it's minus 10p plus c. Okay, so it just tells you what your variable is. Okay, question about the notation. The process that we're doing here is called anti-differentiation or integration. So when something says find the integral or find the value of this or integrate that, it means find its antiderivative. So integration is the process of anti-differentiation. Okay, so then that integration is anti-differentiation. Okay, let's look at something else. I'm going to show you the basic rules here, some of which we already got. The integral of k dx. K is just a constant. It's going to be kx. It's just like if I said k is 5, it was 5x. If k was 10, it was 10x. That's a really easy one, okay? And then you always add this arbitrary c on the end. Whoops, see, I forgot it again. Dr. Carmichael would have taken off points for me, okay? Anyway, but he taught me a lesson. This one says if you've got a constant times a function, you can bring the constant out. This one says if you've got things added and subtracted, you can take their antiderivatives or integrals by just taking the antiderivative or the integral of each. That makes sense because if you can take the derivative like that, you should be able to take the antiderivative like that. Okay, so if you've got a string of additions and subtractions, you've got that. Now, one thing I want you to notice here is that we don't have the antiderivatives of quotients or products. They are much harder to take the antiderivatives of because they were harder to take the derivative of. You had to use a product rule. You had to use a quotient rule. It's hard to undo those things with an antiderivative. We will never see that in that course. You want to do that? Take Calc 2. Okay, Calc 2 is all about anti-differentiation. But the ones we're going to deal with is if we have strings of additions and subtractions, things times constants, and then this is just a special case right here. And then the other thing we have is something called a power rule. We're going to practice this. A power rule is very similar to the power rule in derivatives. Now, when we had a power rule for a derivative, how do we take the derivative of that, guys? What did we do? Just literally, what did we do when we took the derivative of x to the nth? You took, what'd you do with the n? What'd you do with the power up here?
You bring it down in front of the x.
You bring it down and multiply. And then what did you do with the power in there?
You minus 1.
You minus 1. Okay, so that was what we learned about what a derivative was, if it was to a power. So notice the two things that you did. You multiplied by n, and then you took away 1. If you're going to take an antiderivative of that, what's the opposite operation of multiplication, guys? Tell me what sort of, it's division. And what's the opposite operation of subtraction?
Addition.
Addition. Okay, so it makes sense that when we're going to have an antiderivative, we're going to end up dividing and adding instead of multiplying and subtracting.
These seem really hard.
They're not hard. Let me show you. Really, they're not hard at all. I mean, you know how to do everything with a product rule now. Let me show you what the power rule says. It says this, and I wrote it wrong, but I'm going to change it here. It says this. It says that, and I'll have you doing this in 3 minutes, okay? It says that what you do instead of taking away a 1, you add a 1, and instead of multiplying by n, you divide by the n plus 1. All right, I'm going to roll it up and do an example. All right, let's suppose I went back to another one that I already did. Suppose I said 5x to the 4th dx. And we said we can bring a 5 out of this. And now I'm asking you to integrate x to the 4th. So I'm using one of these properties, that's that second property, to pull the 5 out. If it's just a multiplicative constant, guys, you can pull it out. Then I've got x to a power. What does the power rule, we'll call it the power rule for integrals. It says this: add 1 and divide by whatever you get. So when I do that, I get 4 plus 1 over 4 plus 1. I'm going to add my plus c, but that's all I do. Now when I look at it, I get 5 over x to the 5th. That 5 was already there, over the 5. The 5's cancel, and I get the thing, I get the antiderivative. What's the derivative? Check it. What's the derivative of x to the 5th? It's 5x to the 4th. All I did, guys, and this is not hard, all I did was, when I'm doing an antiderivative, I add 1 and divide by that versus multiplying and subtracting. Let's try another one.
So what's the answer? Just x to the 5th plus c?
That's right. Isn't that whose derivative is that? 5x to the 4th. So you show, that's an antiderivative right there.
But do we have to do it that way?
Well, I'm going to tell you that if I get, listen, I set you up here, okay? I gave you ones that you could easily see, okay? But what if I gave you one like this? 7x to the 15th. You know what? That's not as clear cut as, I was giving you ones that you could see you took the power down and took away. I was giving you ones that were easy to see. That was not as easy to see, but it's no harder to do if you've got the power rule. Here's what the answer is going to be. Just pull out the 7. Actually, I'm running out of room here, but I'm going to go this. Pull out the 7 right there. And take the x, it's x to the 15th. What did the power rule say to do? Said to do what to that 15? There's the power right there. What did it say to do?
Plus 1?
Add 1.
Add 1. So it's going to be x to the 16, and then put it over that same number. You're always going to add plus c. Now, I'm going to check it. I'm going to show you that you got the right thing. Okay? My check is going to be find the derivative and see if you get back to where you started. Well, if I were to find the derivative, so we're going to check by finding the derivative, y prime we'll say. If I bring the 16 down, it'll be 7 times 16, x to the 15th, and this was already over 16 for that 1/16 right there. I'm going to scroll it up here, guys. The 16s cancel, and you get 7x to the 15th. So it works. All right, that's really messy. I'd like to do another couple of examples without that. Now, I am going to tell you something right now that's relevant for what I'm going to do next on Monday. What does the plus c really mean? If you start out with the derivative of a function, that means you've got the derivative, you've got the slopes or whatever there. But it would be 5x. If you looked at all the 5x without the c, if you looked at a function y equal 5x, if you let c equal 0 here, it's just a line. If you look at 5x plus 1, it's a line that got shifted up, so it has the same slope. If you looked at 5x minus 1, it would be the line that dropped down, still has the slope of 5. They all have the same derivatives. Their derivative is 5. These are all antiderivatives. This is my generic form of the antiderivative. What we say is that this gives me a family of curves. This right here is a family of curves. And that family of curves looks like y equal 5x plus a constant. All the constant does on these lines is just shift the y-intercept, basically. All right, so I'll talk more about that Monday, but let's do some more examples here. If I said, what's the integral of 2x? You already know it's x squared. That's one of the easy ones I gave you. But pull out the 2. You got an x to the first. The power rule says add 1 to it. You'll have 2 and put it over that 2. Add 1, you'll get 2 and put it over 2. Then the 2's are going to cancel and you'll get x squared. Now, again, sort of on the same note that I picked a minute ago, that's a family of curves. If I just looked at y equal these things, if I looked at it without the c, it would just be this one right here. It would be the one that went through 0, 0. It's a parabola. But if I add 1 to it, it would shift it up. If I added -1 to it, it would shift it down. Here's a family. They're all a family. They basically have the same derivatives, but they go their own way. They go through different points, basically, but they have the same derivative. All right, another example, and then we'll do a few more examples, and we'll call it quits. These are not hard when you get the hang of it. You guys, but now you have a forward gear, which means if you're going to take a derivative of a function, you're going in the forward gear. If you take an antiderivative, you're going in reverse. Now that we've got both of them, you got to be sure which gear your car is in, or you're going to hit something. Okay. So if you know the power rule for integrals and the power rule for derivatives, you can use them when you need to. So look at this one. The 5 is steady, it holds. What's the antiderivative of x cubed? Add 1 and put it over that. It's x to the 4th over 4. Add the plus c because we don't want to leave out anybody in the family. Check. If I want to check it, I'm going to take the derivative and see if I get back where I started. If I brought the 4 down, these 4's, that 4 would cancel. Take away 1, I'd have x cubed, I'd have 5x cubed. Okay, so all I do to check it is take the derivative back and see what it is. See if you get what you got started with. Derivative. Okay. All right, let's look at another one. Now, let me be careful with this. Just the way you had to rewrite things for derivatives, you got to rewrite them for integrals. I've got to rewrite the square root of x. If I rewrite it as x to the 1/2, the antiderivative is going to be x to the 1/2 plus 1 over 1/2 plus 1. And the plus c. I added 1, I put it over that number. 1/2 plus 1 is 1.5, otherwise known as 3/2. Be careful with this. So it's x to the 3/2 over 3/2. If I invert and multiply, it'll be 2/3 x to the 3/2. So all I did there, guys, was use the power rule, but I had to rewrite it. All right, I'm going to do another one. We've got time for a couple more. The 2 just stays. You take -4, you add 1, and you put it over -4 plus 1. Now, guys, I'll put the plus c on in a minute. What happens when I add -4 to 1? What do I get?
-3.
-3. So my answer is 2x to the -3 over -3. If you were to differentiate that by bringing the -3 down, it would cancel. You take away 1, it would be 2x to the -4. That's exactly what you started with. That's all the power rule says.
All right, these are definitely hard.
They're not hard. Wait. Let me give you one on steroids and see what happens. This is my last one, okay, guys? All right, I promise. Okay. I'm going to do all of these.
No, Lord.
But Haley, stop. You're making everybody else worried. Me too. Okay. Look, here's what I got to do first. I've got to rewrite everything. That one's okay. That one's okay. I'm going to rewrite this as x to the 2/3. And I'm going to rewrite this as 3x to the -2. Okay. I need to rewrite them just like I rewrote derivatives. Okay. Now, we'll do this one. What does the power rule for integrals say? It says you take your function, the 2 is just a constant, you add 1. What do you get when you add 1 to 3?
4.
4. So it's 4/4. All I did was add 1 to that and put it over that same number. That's all I did. I know why this is confusing because you're used to doing something the other way, but it's not hard. The power on this one is 1. So tell me what's going to go on the antiderivative. This x to the first, what's going to go here?
X to the second
Yep.
over 2.
Yes. You just add 1 and put it over that same number. You can compute. You can fix it up if you want to. Let's look at this one. This will be x to the 2/3 plus 1, whatever that is. It's 5/3 over 2/3 plus 1. So if I were to rewrite that one, it'd be x to the 5/3 over 5/3. But all I did was add 1, guys. I added 1 and put it over that number. Finally. How about this one? That's going to be the 3 stays there. What happens when I add 1 to -2?
-1.
Good. I get -1, and then I put it over -1. And then I finish up by adding c. Now, your book's going to simplify some of this stuff, for instance, by taking that minus out in front and dropping that x down in the denominator. That's okay. Right now, just practice the power rule for integrals. All of those are going to be similar things on the test. A quick comment. You don't know how to do a quotient. So the rewrite on this one, you need to divide by these things. It would be 2x plus x squared, and that's easy. It would be 2x squared over 2 plus x cubed over 3. You're just adding 1. Same thing right here. You don't know a power rule for something like this. So what you're going to have to do is multiply it out. Okay. So guys, the homework, there's a quiz due on differentiating exponents. It's not hard. It's the stuff we started class with. And then try some of this homework. We're going to be doing it again on Monday. It's just that you guys are going to be ahead of the game because everybody else is going to be scratching their head saying, what the heck? Okay.
So the quiz is due on Monday?
Monday before class, if possible. Okay. I would suggest doing that first. Go to Moodle, look for the exponential derivatives quiz.
Is it on this hard stuff?
No, it's not on what I did today. It's what I did yesterday. But I
okay, that should be fine then.
Oh yeah, no, yeah, that'll be fine. And then we'll have another one on this maybe Tuesday or Wednesday, something like that.
Tuesday.
All right, Wednesday. It's just pushing it further back. Look, guys, what I'm trying to do here, we're running out of time. I want you to do really well on this next test. It's not much material. So I'm going to give you quizzes on everything that's going to look like what this test looks like. Okay? We're going to have a really short test at the end. Okay, y'all have a good weekend, and I'll see you on Monday. A good day.
Right.
Monday. Bye.
Bye.
Bye-bye.
Bye-bye. Nice.